which is 5x squared minus 8x, and then e, and it's x squared minus 4x. How was this different from what we did in class?
It wasn't really. I was just having a little bit of problem simplifying it.
That's
so
fine.
I wasn't sure if I did it
oh,
right.
yeah, absolutely. Let's do it. So, of course, we have to use the product rule. Function 1, function 2. I'm fine if you don't like this method and use your own twisted. The functions, it's the same thing. I accept that. It's perfect. Okay, so the first function prime, I get 2x minus 8. And then I copy x squared minus 4x plus. I copy the first now. And I differentiate the second. Remember, e to a function prime is e to the function times the function prime. Pretty much with e to the x. E to the x prime is e to the x times x prime. But why don't I have to write x prime?
Because x prime is 1.
That's it. There is no need. But it's the same thing. Thank you. So then e to x squared minus 4x times this function prime, which is 2x minus 4, times 2x minus 4. So
in the beginning, just to clarify, do you mean 10x minus 8 because it's 2 times 5?
Oh, thank you so much. No, I was asleep at the wheel. No, I wasn't trying to see whether you were paying attention or not. No. No, it was not a tricky thing. I just, yes, I talk too much. That's why. So now I have to go back and check everything. So it is 10x. Thank you so much. So 10x minus 8, yes, times the second function plus. I copy this first, and now 2x minus 4. Okay, thank you. So e to x squared minus 4x, and let's see. There is nothing else I have to multiply here, so this is 10x minus 8. But now these two have to be multiplied because this is a product, 1, 2, 3 factors. So 2x times this, and it's plus in front, so I don't have to worry about signs. I copy exactly the sign I see. 2x times 5x squared is positive 10x cubed. 2x times negative 8x is negative 16x squared. Negative 4 times 5x squared is negative 20x squared. Now this is positive, and this is 32x. Okay, I hope I'm okay now. Now, once I make an error, I have to check everything. So this is indeed 10, this is negative 16, this is negative 20x squared, correct? And this is positive 32, correct? Okay, so e to x squared minus 4x. Let's see what we have here. So this is the first one in descending order. Now we have these two, negative 16, negative 20, negative 36x squared. Now we have these two, so positive 42x, and now this is alone negative 8. Is this okay?
Yes, thank you.
Thank you. Other questions? Anything else? We want to look at anything else. Anything you worked on, anything.
Can we go over number 34 on page 304 also?
Yes. 34 on 304. Very good. Let me share. Here it is. This one.
Yes.
Okay, that's why I did 33 in class. Let's do 34. So g of x equals e to 3x divided by x to the 6th. And we're asked to differentiate. So this time we're going to use the quotient rule, 1 divided by 2. So g prime, I square the denominator, so this is x to the 12th. I differentiate the numerator, e to a function, prime is e to the function times the function prime, and times the denominator, and then minus, the numerator stays, times the denominator prime, which is 6x to the 5th. I will factor out e to 3x.
You're still sharing your screen.
Oh, no. Sorry. Okay, let me do it again. So I'm using the difference. I'm using the quotient rule. So the denominator has to be squared. When we copy the base, when we have x to the sixth, everything squared, we copy the base, multiply the exponents. So now when I differentiate e to a function, I get e to the function times the inner function prime times the denominator, then minus the numerator times the denominator prime, which is 6x to the fifth. So now I continue. I will factor out e to 3x first. Then I can also factor out a 3, because it's 3 and 6. And I can also factor out x to the fifth. And let's see what is left. 3 is out, e to 3x is out. From x to the sixth, I took out x to the fifth, so there is only one x left. Minus. From 6, I took out a 3, so there is a 2 left, and x to the fifth is out, e to 3x is out, and that's it. Only now I'm allowed to simplify. So 12 minus 5. So this is x to the 7th power. And this is the final form. 3 e to 3x, x minus 2 over x to the 7th power. Is this okay?
Yes, thank you so much.
Thank you. Other questions? Do we want to see? Yes?
Can we do number 10 on page 279? It was from 2.8. I just had a little bit of trouble.
Let's do it. Okay, so I'm going back to 279. 279. And it's problem 10. Good. So x to the third minus x squared y squared equals -9. And the given point is 3, -2. Perfect. So we're asked to find the equation of the line, or I'm sorry, is it the equation or just the slope? Find the slope, just the slope. Okay, perfect. So once I have dy over dx, I will plug in x equals 3 and x equals -2. This is the question. This is what we're asked to find. At this point, I do not have dy over dx. Don't even look there. So I differentiate the left-hand side. I differentiate the right-hand side. It turns out that I can solve this one for y, but it will be more difficult if I did solve and then find dy over dx. So it's better to use implicit differentiation. So I differentiate x cubed to get 3x squared. Now here, be careful because this is a product. Keep the negative outside if that's what you want to do, or just remember both terms have to be negative. It's up to you. 2x times y squared plus x squared, but now this is 2 times y times dy over dx and equals 0. So this is completely separate. Maybe I should write it one more time for everyone to make sure it's not. So 2x y squared plus 2x squared y dy over dx equals 0. Is this step okay before we continue?
Yes.
Perfect. So now I will distribute. Again, many times I'd like to do 2 steps in one, but here I just want to emphasize that you have to be careful because we may forget to distribute here if we don't put parentheses. It's up to you. If you know what you're doing, parentheses are not required, but you have to distribute at once. So this is 3x squared minus 2xy squared. This will be negative. I'm going to already move it to the other side, and it becomes positive. So 3x squared minus 2xy squared minus this, but this is the only term that has the variable, so it has to be moved to the other side. When I move a term from one side to the other, all I have to do is change its sign. It would have been negative, but I'm putting it on the other side so it becomes positive. So now I will solve for dy over dx, dividing all this piece by the constant in front of it, so to speak. So 2x squared y, and the top has an x in common. So I have 3x minus 2y squared. Why? Because I want to simplify if I can. So then finally dy over dx will be 3x minus 2y squared over 2xy. This is when I plug in now x3 and y equals -2. Okay, so 3 times 3 is 9. 2 squared, 4 times 2, -8, because this is positive and times -2. The denominator, 3 times 2 is 6. 6 times -2 is -12. So the numerator is 1, the denominator is -12. The simplified form is -1 divided by 12.
Thank you.
Thank you. This is the only way when we do work and then we ask and we go over. That's the best way. That's why I'm doing this. It's very time consuming to grade and everything, but I have to do it because otherwise you may not be in the clear with what needs to be done every step and how the solution needs to be presented, etc., etc. So I always do this with my classes. I always give a little bit of a written homework. Good. Next question. Very good questions. Anything else? Anything from my lab math? Anything? If not, I'll move on to 3.2, the last section. Let me know. Do I start 3.2? Anything else? Okay, then 3.2, logarithmic functions. Logarithmic functions. Remember last time we looked at the exponential function, and it has two shapes. One for the base greater than 1, and the other one for the base between 0 and 1. And you could say, how come that I cannot have f of x equals 0 to x, or 1 to x, or -3 to x? Why? Because as you see, the base is strictly greater than 1 or between 0 and 1, not 0, not 1, not negative, not 0, not 1, not negative. How come that these are excluded? They are excluded from the exponential function because we would not be able to define its inverse, -1. Okay? Its inverse function is log base a of x. A is the base for the exponential as well as for the log. So this base for the log function will not exist if it were, or the log function, I should say better, will not exist if the bases were 0, 1, or negative. That's the reason why we have to exclude these possibilities from the exponential function. And let me refresh your memory how it looked like. This one is the dangerous one that we are facing as we speak, with a base greater than 1. And this one is with a base less than 1, decreasing on all its domain. It's a friendly function overall because I don't have to worry about its domain. As you see, the domain is already numbers. However, the range, can anyone give us the range of the exponential? Pure exponential. Because I can show you exponential functions that do not have the same range with the pure one.
Would it be 0 and then into infinity?
Yes, I don't think that this is a good color, so let me just graph it again. Yes, of course. Yes. So the exponential function, we say, is defined on all real numbers, and it has range. So this is defined, this is the domain, and this is the range, 0 to infinity. Obviously, the logarithmic...
Sorry, I think you're muted.
How did that happen? What did I do?
You
Sorry.
went away.
Oh, okay. I didn't realize that. I'm looking down, so thank you. Sorry about that. So this is the exponential function with a base greater than 1, increasing on all its domain. Tiny base between 0 and 1, decreasing on all its domain. Okay, as you see, this is a horizontal asymptote to negative infinity, and this is a horizontal asymptote only to positive infinity. Okay, so we say that the exponential function is a friendly function, domain all real numbers, taking values, range 0 to infinity, exactly what you gave me, 0 to infinity, for the pure exponential. So now its inverse function, which is the log function, will be defined exactly opposite. That's the definition of the exponent of the inverse function. If the function takes this to this, the inverse will take this back to this. So now the domain is 0 to infinity, and the range is everything. So now I do not call this function friendly. Why? It has restrictions. I have to worry about it. Are there other functions that I have to worry about? Yes. The square root, I have to worry about it because it can only be defined on positive or 0. Is there another? Yes, 1 over x, because x cannot be 0. So these three functions are functions rational, radical, with an even index, and log. They are functions with restrictions. They may or may not, but these are functions that I have to worry about. Okay, how do I graph the function and the inverse on the same coordinate system? Whenever I do that, I have to graph the line y equals x first. Y equals x. Y equals x is the line that bisects, divides the first quadrant into 2 equal parts and the third quadrant into 2 equal parts. The same here. And now all I have to do is reverse the graph of the exponential with respect to y equals x. So this will be the graph of the log. What about here? If I do the same thing, right? If I do the same thing, this will be the graph of the log. They have to be symmetric with respect to y equals x. So here it is. Notice that this graph does not cross y equals x. Of course, the log will not cross y equals x. And it has to have the same base with this one. For example, if this is common log 10 to the x, this must be log x. We don't write the base if it's 10. So if this is base 10, this must be base 10. If this is base 5, will not be inverse of the log of base 10 of x. No. So for these two to be inverses of each other, they have to have the same base. And the same here. But now here you have to be careful, because the function crosses y equals x, that must be a point of the inverse as well. Because here I have 1, 1, 2, 2, 3, 3, 4, 4. If you reverse them, you still have 1, 1, 2, 2, 3, 3, 4, 4. So this is the graph of the inverse function. So if this is, for example, let's say 1/2 to the x, this must be log base 1/2 of x. And there are several properties of the log function. And we can go over those. Just remember, log will join the other two functions with restrictions. The rational, radical with even index, log. Log, radical with even index, rational. They're not friendly, I call them. Okay, so some properties here, and we know that log of a product in any base is the sum of the logs, but also vice versa. If I have log in the same base, they must be the same. Log of 5 plus log of 3, I can write log of 5 times 3. So it goes both ways. That's one property. Here's the second one with a ratio. Anyone remembers what the ratio is all about? What does it do by comparison to that?
Subtracts, doesn't it?
Exactly the same thing. Log x minus log y. Again, it goes both ways. If I have this, I can condense it into this. If I have this, I can expand it into that. And one more, log base x raised to power b. This goes in front as a factor. Factor meaning it multiplies log. B times log x. And of course, this goes back and forth. If I see a number that multiplies a log, I know I can put it back as a power. If I see log applied to a power, I can take the power and put it in front. Exponential notation, I can put the power in front. Another important property is that log in any base of the base is 1. And log in any base of 1 is 0. Also, something very important here is how to convert an exponential equation to a log equation and vice versa. This is very important. So if I have a log equation, I can convert it into an exponential equation and vice versa. And this is really very important to remember. Log base a of x is y. This is a log equation. I have log in it. Once I read log base a of x equals y, I know it's a log equation. And this is equivalent to, and here's how we start. We always start from the base and go counterclockwise. A raised to y equals x. A raised to y equals x. Not a times y equals x. A raised to y equals x. Finally, how do we differentiate? So we have two major, where is my calculator? Where's my calculator? Oh, I have the program. So let me share for a second. So right here, there is a, so see these two keys, they are together, 10 to the x and log. Why? Because these two are inverses of each other. 10 to the x and log base 10. Also, these two are inverses of each other. So this is common exponential function, common log function, natural exponential function, natural log function. I'm going to write all three again here on paper. So the common and natural. So the common is the 10 to x, and its inverse is log x. The natural is e to the x, and its inverse is natural log, natural log x I meant to write. What will I do without whiteout? I don't know. Natural log x, of course. So obviously this is the common exponential, this is the common log, natural exponential, natural log. I have to let it dry for a second. So now, let's see how we differentiate. Your book does not show anything about, I'll show you how to differentiate these two, but we're not going to use them because I didn't find any example in your book, and I'm just going to stick with it. So we know that e to the x prime, we've done this, this is the nicest possible. Now, what about natural log x prime is 1 over x. Okay, 1 over x. Natural log prime is 1 over x. Now, what if I have a function, which we did several times with e to the x, instead of e to the x? Why did I write 2 over there? This is my page 4. This is my page 5. Okay, so one more time. E to the x. e to a function prime is e to the function times the function prime. Same thing, natural log of a function prime is 1 over the function times the function prime. Versus the simple pure exponential, e to the x prime is e to the x. Again, we should write times x prime, but it's 1. Same thing here. Natural log x prime is 1 over x. I should write times x prime, but it's 1. So we're going to encounter many functions with log function, with log, and we will be asked to find the rate of change in different situations. This is the end of the material for test 2. So let's see which page I want to be on, 319. And I let you choose. You choose first, and then I'll choose.